now let us look at the general principle of inclusion exclusion, where you may not have just 2 sets or 3 sets. What if you have any number of sets? Okay. So, suppose I have n sets in general. So, this is a general principle. To understand the general principle, the general case, let us just look at the situation where we have 4 sets. Okay. Let us now call them A1, A2, A3, A4, and now what are the various possibilities? You can have, say, things which are exclusively in each of the AIs, elements which are exclusively in the AIs, or things which belong to 2 of the AIs, exactly 2 of the AIs, or exactly 3 of the AIs, and so on. So, to understand the picture, so it's kind of complicated to try and draw a picture of the kind that we drew with 3 guys. Also putting the 4th one in makes it much harder to sort of figure out what is going on. So, instead of trying to do it in terms of the picture, let us do the following table. Okay. So, I am going to understand the various regions that I can get purely in terms of a table. So, let us do this. So, what is this table? I am going to have 4 columns. I am going to say A1, A2, A3 and A4. So, those are the 4 sets, and what are the rows of my table? I am going to have 1 row for each element in my set. Okay. So, here is my table. The elements of my set will be along the rows. So, the set probably has lots of elements. So, I do not know, I will call them x1, x2, x3, x4 and so on. So, I go until some xp maybe, and so we make a table like this, and what do we record in this table? For each element xi, we will put a 1 if xi belongs to the corresponding aj. So, what I mean is if the ith element xi belongs to the jth set aj, put a 1 in the table, put a 1 in the ijth position of the table. Okay, ith row jth column, put a 1, else put a 0. So, what does that mean? So, if x1 for example belongs to a1, so let us say this is our set a1, x1 is here and in not in any of the other AIs. So, a2, a3, a4 are here, and if x1 does not belong to any of the other AIs, I will just put zeros on the other ends. Okay. Now, if x1 maybe belongs to a1 intersection, if x2 the next element belongs to a1 intersection a2, but it does not belong to a3 or a4, then I will say okay, it is an a1 and a2 but not in a3 or a4. Likewise, there could be an element which is in a1 and a4 but not anywhere else, or some other element which is in 3 of them but not in the 4th. There could be other elements which are in the full intersection, there could be elements which are in all 4 and so on. Okay. So, these are my various possibilities. So, we put a 1 in the ith row jth column of this table exactly when the element xi belongs to the set aj, otherwise we put a 0. Okay. And now, if you look at this table, how many different possibilities are there, how many different configurations are there? Something can belong to exactly one of them, for example here to a1 alone and to none of the others, or it can belong to a1, a2 and none of the others and so on. So, the number of different regions in some sense that you can get is the same as the number of sequences of zeros and ones with of length 4. So, how many sequences of zeros and ones can I write with of length 4? It is exactly 16, right. Each of these sequences of zeros and ones, each position I have got 4 positions, and each can be either a 1 or a 0, 1 or 0. So, I have 2 choices for each position. So, I have a total of 16 possible sequences of zeros and ones of length 4, and those 16 in some sense correspond to the different possible x's, which are, they can be in either in one of them or these 2 of them but not in the others and so on. But out of these 16 there is one possibility which is not allowed, which is that we are looking at elements which belong to at least one of the AIs. So the possibility 0 0 0 0 will never occur in what we are doing, because this possibility means that the Xi is not in any one of the AIs. So there are of course also instances where we can have that is when we have one larger ambient universal set, some bigger set which contains all of these 4, let us call it omega, and suppose we are also interested in looking at the complement of the AIs. You are looking also at elements which are in omega but not in any of the AIs, then you would also get this possibility 0 0 0. But I mean it's just a different version, different formulation. So for us we will not do that, we will assume we are only looking at the union A1, A2, A3, A4. Okay, so let us get rid of omega for now. Okay, so let us come back. So we do not have 16 possibilities, instead what we have are only 15 of them. Okay, now let us write out what the inclusion exclusion formula should look like in this case. So what it says is again inclusion exclusion formula or theorem if you wish, says that the cardinality of the union A1 union A2 union. So in general I will assume AN. So I gave you the example of 4, but let us do it for any n be any number 2 or more, and let A1 A2 AN be any finite sets. Then the cardinality of their union is the following. So you first add up the cardinalities of all the AIs. From that you subtract the cardinalities of their pairwise intersections. So what this means, I and j run from 1 to n, but I and j are distinct, I is not equal to j. Okay, so you take different pairs. So one way of ensuring that we are only taking, we do not want to count I equals 1 j equal to 2 as being different from I equals 2 and j equal to 1. So one way of writing this in summation notation is to say, look at summation I j going from 1 to n with I smaller than j. Okay. So I take these pairs. Now to that I have to add cardinalities of triples. So let us use ijk for now. So here again ijk then k and so on. So minus cardinality of quadruples, etc., etc. And finally what is the last term that we are going to get in this setting? It is the intersection of all n of them together. Okay. And observe the coefficient in front is either a plus or a minus, and the correct power is minus 1 to the n minus 1 times the cardinality of A1 intersection A2. So that is a very last term in this whole series. Okay, so that is the same pattern, it follows the same pattern as what we have seen for 2 sets and 3 sets, and the general case is no different, it is just the same formula extended in the obvious way. Okay. Now let us try and prove this, or at least try and convince ourselves of the proof. So let us try and understand what is it that we are doing here, what is the right hand side calculating. So proof, or whatever what is the idea of the proof. Okay, so that is best understood by looking at this table. Let us go back to this table, and this is in the case of n equal to 4, but the basic ideas are already here. So what is the first term of the formula telling us? Let us go down back to the formula. So this is summation ai, right. So we are trying to find the sum of the cardinalities of the individual AIs. What is it in terms of this table? So here is the table again. So, for instance, the cardinality of A1, the very first set, is just the following. You just add all the ones in the first row, wherever you see ones. I mean, some of these could be zeros also, but if you add all the ones, the sum of the first column is exactly the cardinality of A1. The sum of the entries in the second column, so this sum is exactly the cardinality of A1. The sum of the second column is the cardinality of A2. Here again you add all the ones here, you get A3, you add all the ones here, you get A4. Okay. So, that is what the first 4 terms of the right hand side of the inclusion exclusion formula tell you. It is just the sums, the column sums of this table. Okay. Now, let us see what does the next term tell us. What is the next term? Well, it looks like cardinalities of intersections of things 2 at a time, pairwise intersections. So, for instance, if you are looking at the cardinality of A1 intersection A2, how would you understand that from this table? Well, here is what you would do. You would look at those rows of the table. For example, look at this row x2 or the element x2. Look at those rows of the table where there is a 1 in both these entries, in both these columns. Okay, so maybe x2 has 1s there, and let us say maybe some other element x5 maybe has a 1 in both those places. Okay, so then you look at that element and so on. Okay, so what you want to do now is to find those rows of the table in which you have got 1 1 occurring in the first 2 columns. Okay, look at all occurrences of 1 1. Now, when you see a 1 1, what does that tell you? It tells you that that corresponding element xi is in both A1 and in A2. Okay. Similarly, if you want A1 intersect A4, then you look at elements such as x3 which have got 1 and 1 in the first and fourth columns. I do not care what the other column entries are. I could have 1 1 in the first and fourth, and I could have maybe even zeros or ones in the second and third columns. That does not matter to me. Okay, so since I am only interested in the intersection A1 intersect A4. Okay, so this is really what the various terms of the right hand side tell you. Now, what we will do is we will try and count the contribution of every single element xi to the sum on the right hand side. Okay, so let me write this down, then we will see what we mean by counting the contribution. So, the main idea of the proof is the following, is count the contribution, that is the keyword here, of each element xi to the sum on the right hand side. So, I am going to show that the right hand side is equal to the left hand side by analyzing the right hand side and understanding it better, and we are going to do that by focusing on an element, that is focusing on a row of the table, and we will ask, okay, that element xi that I am interested in, what is its contribution totally to the right hand side of this formula. Okay, now what does that mean? So, let us focus then on the table of, so I have got that, here is my table. Okay, in general I have got A1, A2, A3, some AN here, those are the column headings, and my focus is only on a single element, right. In other words, I am looking at a single row of this table, the contribution of the element xi. Now, when I look at this row of the table, what do I see? Well, I see some zeros and ones, right. So, if xi belongs to A1, A3, it does not belong to A2, maybe it does not belong to A4, etc. So, I see some zeros, ones. Okay. So, what I will do is I will just collect all the ones. So, let us do the following. First, let us collect the ones. So, what do I mean by that? Let us define a set. So, define T to be all those j's, all those positions, all those column numbers such that xi belongs to aj. In other words, take the column numbers with ones in it, column numbers where ones occur. Okay. So, the column numbers where ones occur are exactly the sets ai. So, in this case x belongs to a1, a2, it belongs to a1, a3, so it does not belong to a2, it belongs to a1, a3, an, right. Maybe there are some ones in the middle, I do not know. Okay. So, the column numbers where ones occur is what I am looking at. Now, what is the total contribution? So, let us look at the right hand side of the inclusion exclusion formula. The first term is the sum of all the a's, right. Let me call it aj instead of ai, so as not to confuse with the other I. So, j goes from 1 to n in this case. So, in this term summation of the cardinality of the aj's, so remember that was just supposed to be, I had to count, I had to add every single column, the ones in every single column, right. So, this is nothing but sum of all the ones in the table, but I am only going to contribute, only going to focus on the row I, the ith row. So, let me only look at what is the contribution of the element xi to this sum. In other words, what is the contribution of the ith row to this sum? Well, the answer is it is just the number of ones in the ith row, right. And what is the number of ones in the ith row? That is just, so this is the number of ones, that is just the cardinality of this set T. T is just where the ones occur. So, let us give this cardinality of this set T some name, let us call it maybe small t. So, small t just refers to the cardinality of the set capital T. Now, let us proceed. So, we have figured out what the contribution of the sum is, the contribution of xi is to the first term on the RHS. So, let us look at the second term on the RHS, that was cardinality of pairwise intersections, okay, j less than k. Towards this sum, what is the contribution of xi? Well, the answer is you have to see, right. I want to figure out how many pairwise intersections will xi contribute to. Well, that is equal to the number of ways in which I can find pairs of ones from these t ones that I have. So, how many ones do I have in the row here? I have exactly t ones. Now, what I should do is I should pair these t ones in all possible ways, right. For example, here I know that this element xi belongs to a1 intersection a3, because there are ones in those two guys, I can pair them up. It belongs to a3 intersection an, for example, and so on. So, the contribution of xi to these pairwise intersections is nothing but the number of pairs that I can choose from among these t ones that can be chosen from these t ones in that row, in the ith row. Okay, and now we know how to choose. I have to choose 2 out of those t ones, and that number is exactly the binomial coefficient t choose 2, those many ways of choosing 2 ones from the t ones. Now, we keep going like this. So, if you look at contribution to triples, so contribution of the ith row xi to sums of cardinalities of triples aj, ak, al over all j, k, l. So, in how many ways, how many contributions will I get towards intersections of triples, well again this is nothing but I know I have to pick 3 ones out of the t ones. Any 3 ones I pick, I will get a corresponding set. If I have j, k, l, 3 column positions where there are ones, then those many different triples, intersections of triples will contain the element xi. So that is t choose 3 and so on. So now you can see the general pattern. So the total contribution therefore, so it is just these binomial coefficients will turn out to be, that's however a sign, remember. So the first term was t, which is the same as t choose 1, minus, so pairwise intersections is a plus, intersection of triples is a pairwise is a minus, triples is a plus, quadruples is a minus, and so on. So there are these many ways of choosing xi. This is the total contribution of xi to the RHS, and what is the final term? As you remember, it is minus 1 to the n minus 1 t choose n. Okay. But observe in practice, what do we know? There is something that we should observe about this. T is the number of ones in the ith row. So t is at most n, right? N is the total number of columns. So what this means is that even though this sum looks like it is going all the way till t choose n, it may stop somewhere before, right? If t is strictly smaller than n, then this will go, how far will I go? So I go till, there will be a term minus 1 to the t minus 1 t choose t plus t choose t plus 1 t choose t plus 2 and so on, but all terms after that stage are all 0. So all these are 0 if t is strictly smaller than n. Okay. So in general what will happen is that if I have t choose any number k bigger than t, as soon as k is strictly bigger than t, those terms will all vanish. Okay. Of course, if t is equal to n, there will not be anything vanishing, all the terms will occur till the end. Okay, anyway, so what I mean in this case is that I can rewrite this contribution as a sum until this term alone, until minus 1 to the t minus 1 t choose t. Okay. Now observe, this is something that you have already seen when we looked at the binomial theorem, or a consequence of the binomial theorem was the following, that this alternating sum of binomial coefficients, you take 1 minus t choose 1 plus t choose 2 minus t choose 3 and so on, you sort of keep doing this alternating sum till, I mean the last term will be t choose t, it will come with a plus or a minus depending on, so it will be minus 1 to the t choose t. We know that this sum is a 0, right. So recall that by the binomial theorem we know that this alternating sum is 0. So what does that mean? It means this is not the sum that you are saying here, the total contribution is actually everything except for the 1. So this term here, this is sort of what you are seeing on the as the total contribution, so that term is actually equal to 1. So we conclude, so let me rewrite it like this, I will take all those terms over to the other side, then so this ends then at t minus 1 once I take it to the other side. Okay. So this term, the total contribution of xi to the RHS is exactly the number 1, that is by the binomial theorem. So therefore this is now the main conclusion, total contribution of xi to the right hand side. It was a complicated sums of pluses and minuses, but the final answer just turns out to be the number 1. Okay. Now that is more or less the end of the proof, because observe what this means is that every element xi in your set contributes a 1 to the right hand side. Okay. And what I am doing is I am adding over all the rows, right. So since I was when I was thinking of it as this table, what I am trying to say is that for every row of the table I will contribute, I will take those numbers, I will see what is the cardinality of the set is minus the cardinality of the intersections and so on, blah blah blah. And now I am just figuring out what is the contribution of each row of the table to this sum. Okay, so each row contributes a 1, each row of the table therefore contributes 1. So, the total contribution, therefore total contribution of the whole table is what we are computing. So, total becomes equal to the number of rows. So, what is the number of rows? So, equal to, and there were as many rows of the table as there were elements in your union. For every element of the union we had a row of the table, right. So, that is your final proof. Okay. So, this what this establishes is, I hope at least the basic idea of the proof is clear, if not the details themselves, but what this establishes is that the formula for inclusion exclusion in general for n sets is more or less the same as what you would expect based on the examples of 2 sets and 3 sets. It is just the extension of that formula.